Hi, welcome back to Book Club. We're now in chapters 5, 6, and 7. And that might sound fast, but again, the joy of this book is really in the examples. So make sure you're reading, you're digging through, right? This book club will only, I think it's only going to be like 5 episodes to kind of give you the wave tops and hit the high levels, the concepts. The rest of it, dear reader, is up to you. Go dig in. This book is amazing, especially all the examples, and work through all it. It's really where this thing hits the road. And so, chapter 5, this is going to be really funny, but chapter 5, I'm going to call off design. All right. And I'm going to put big fat, I'll put in different color quotes here. Big fat quotes. Like I said, a little bit in the last video, off design is basically where these jet engines live. Okay. It's never just some perfect conditions, which is what you would need. Okay. Because in the end, you have basically these issues, which is your jet engine. It depends on altitude and speed, right? So altitude, and I'll say Mach number. Why? Because that's going to drive the temperature, the pressure, as well as that Mach variable, which everything falls out of this. Okay, and then it also then your throttle, what we call throttle, is nothing other than adjusting your fuel to air mixture. Remember F back in the day. Now that's going to set your T4, and then you can think of setting your T7 with your afterburner, if you will. I'll just say AB is going to set this one. So your two fuels, fuel in the combustor, fuel in the afterburner, are going to set those two temperatures, and that's your limit that you're going to pay attention to, right? So this is your turbine exit temperature, and this is your afterburner temperature. All right. And then the only other control you may have as a pilot is your nozzle ratio. If you have a pilot, the system can adjust it. It's usually automated. It's not that pilots are sitting there jacking with their nozzle ratio. It's usually on a schedule. That's what they mean, based on pressures and things like that. Okay, this is going to help set that P0 and P9 configuration. Again, back to that jet efficiency is important. And everything else is areas are fixed. And so the consequence of that we'll show here in a second. But where I wanted to start off with this then is basically because of all this, as two really good graphs that I wanted to show you, and this might swallow my face completely. Yep. Oh, not too bad. All right. The first one, Embry-Riddle Aeronautical University has this book online that's Introduction to Aerospace Flight. I think it's actually a phenomenal book. It covers so many things. I probably won't go do that as a book club because I'm already doing a bunch of different portions, but it really is a great, and this graph I've not found sort of anywhere else. So I love what they've done here. It's basically on log in terms of altitude and then flight Mach number. And what makes this so great is it really sort of highlights this regime here, where kind of stall and buffet would get you. Like it's pretty damn slow, and so this is the domain of helicopters, right? This is where helicopters just crush it. This is these sort of low speed vehicles, right? And so I have my fixed wing pilot's license, but I've done about 20 hours in a helicopter, and I will say the helicopters are way more fun to fly than I haven't finished my IFR to where I've really turned into the ability to kind of fly whenever I want, sort of thing. Then you have here sort of your piston engine limit at that Mach number, your turboprop limit. This is sort of the domain of airliners, and then so yes, turbofan can get you up to that sort of that Mach 2.5 I kind of kept referring to in the past, where sort of hey, at these temperatures your engine's gonna melt. Right? There's that stall and buffet limits of the aircraft itself that kind of is going to give you this altitude limit, and then you have on the right there's your structural limit. There's that thermodynamic limit, which is, again, I love this better because it's not just a flat line like I was showing you before. It sort of leans off, and then you have sort of here the domain of rockets. I love it. Then orbital velocity is actually Mach 25. So it sort of makes it appear like it's Mach 10 here. It's really Mach 25, which is it's probably the right line. It just without the dash marks, you can't tell that on the log scale it's really at 25. So this is just a great diagram. Now a lot of people, it'll highlight, a lot of people will look at this and be like, oh yeah, you can breathe air on your way to space. You can. That's this whole idea of scramjet, single stage to orbit. There's other stuff in here. Okay, on scramjets, there's a temperature limits based on like the air is getting crazy hot. So even like burning fuel where it's actually adding energy to the air becomes really challenging. So anyway, I'm not going to get into scramjet world, but just it's know that it's pretty brutal. And honestly, this is the standard thermodynamic. There's another one that pops up when you start accounting for skin friction, which I don't know that curve is accounting for skin friction appropriately. All right, it really starts eating your lunch. Okay, all right, but this is a great diagram. Now the other one, I actually can't find the source. I was Googling for a right picture that looked like this. I don't like dropping up things here that I don't find the source to. So I'll sort of put it out to the internet. It just says 5.2 adapted from 1. This is the only picture that showed up on the internet. Now, I would love to know where this picture sits. So one, I can cite it properly, but this is a great, this is basically your engine thrust to weight ratio, because there's your sort of jet engines at 7. Afterburners usually give you double the thrust for a lot more fuel usage. That's usually the way it works. And then ramjets here, I would love to know where this curve for ramjet is really coming from. Anyways, so help me out, dear internet. Help me figure out where this picture is coming from. I thought maybe because of the blue letters here, I thought maybe it was Raymer. This looks like an AIAA book. I just can't figure out which one. So please help me out, dear internet. Okay, those are kind of two great. Kind of cleared out. So two great pictures to kind of help out here. Okay, and the rest I'll sort of draw by hand to sort of make sure I can highlight the right stuff. And so from all of this off design, what you then have is a couple different things. So you might look at the compression ratio of the fan versus m dot corrected. Now this is where I know industry has got these conventions, and I really hate them. It's not. If you're in the industry, it's okay. Some of the stuff is like industry does things that they may have done in the 50s and 60s because you can't have computers and you can't calculate all this stuff. But this I'm not corrected one, it really drives me nuts. I'll just write it here because it is basically this. It's the pressure at standard times area over temperature standard times this thing called the mass flow parameter, okay? And so it's supposed to be correcting the mass flow parameter back to standard pressure and standard temperature. Now, maybe this is from the jet engine testing world where you have these mass flow parameters of, hey, the engine's at this altitude, but we're testing it at sea level. I actually don't know the history behind this. I'll go dig a couple of my friends who have worked in this industry, and I'll make a note below if I find out where the root of this really came from. Because then you then ask, well, what the heck is the mass flow parameter? What you see is that it's just m dot times the total temperature, total pressure, and the over area square root's only on the temperature, which basically undoes it. So the best as I can tell, the m dot corrected is just the m dot, unless I'm missing something. So this is the kind of stuff that it bugs me. I don't really understand why. But the main point of this was that here is your sort of stall surge line, and then you're going to have kind of performance of your fan, and each one of these is percent, and then capital N. This is your RPM of your engine. So back to what you can actually control. So your aircraft, you can fly it to different altitudes and Mach numbers. Your throttle is throttle. It's fuel. Okay, but what a pilot is going to do is going to sort of do this on throttle, and he's going to the result of throttle is going to be an engine RPM, and that's what the pilot's going to see. And so they're going to effectively adjust and talk about like I'm at 100% throttle. I'm at 50% throttle, and that would actually mean here is RPM, not necessarily fuel load. Okay, and then there's the control system is then taking that input and then converting it to a fuel flow rate, things like that. Okay, so it's a kind of a scheduled system. So this is what's going to happen here. Okay, and that's on the fan, and then basically the same sort of thing. You'll see the picture on overall compression ratio, which again I'll draw this sort of line. That's the stall surge. Your compressor can stall. It's a blade. We'll get into sort of in the next video on components. But your compressor is a blade. You can stall it, okay, and you can surge it. So then again, here are sort of these performance characteristics of efficiency. So these are curves of that sort of engine efficiency, where you might want to sit there based on your off design. Again, the altitude and Mach number you're at, you may actually be sitting on these weird systems where, again, I'll draw these kind of in orange, where this is your percent throttle, your RPM as a percentage. Okay, so that's one. Other off designs. And this is now kind of into chapter 6. So I'll do it here at the bottom, where hopefully you can still see. And you'll hopefully with me you'll kind of laugh. It's like, what do you mean these are off designs? Like, yeah, well, okay. So here's your engine. Right, there's your there's your blades and there's your core and all that stuff. Okay, well, this is your inlet, and what's actually happening, the air going into your inlet is not it's not the same area. Okay, so it could be down like that. At some speeds it could be up like this. Right, so it's actually it's your inlet, and then there's also the drag associated with your inlet. Okay, which it's the integral going from 0 to 1 of P minus P0, the area. Okay, and so your inlet drag can actually drive a whole lot of things. Okay, and so what I'm going to show here is sort of that inlet drag versus Mach number, and it can kind of show you a couple of these different choices, and honestly, the drag numbers here might be only like 4 to 5% if you have a very thrusty engine. So that would be 4 to 5% if the way they say that, if your F over M dot A is 4. So that would be like a high thrust F-16 style engine. Might be 4 to 5%, but could be as big as 50% if you have sort of a wimpy engine. If it's this large, I think 0.5 sort of a thrust. It's like the thrust compared to the flow rate of your. Basically, it's a way to show engine size, like frontal area, effectively, the engine size. So it could be pretty damn large. All right. So that's inlet. That's on like regular subsonic inlets, and then as soon as you go supersonic, they cover in this chapter as well. Okay. So you can have again here's your inlet. So the F-16 basically has a mouth inlet, and then you get these shocks. Okay, the shocks that kind of stand up, and then you get normal. And so it's a very simple design inlet, but it builds up quickly, and then you can also get a shock that runs external off your engine, of course, right? So that can also highlight your drag as well as affect your compression. And then there's internal compression, where you have sort of a ramp. Okay. Kind of a ramp like that, and you get sort of that shock here, and then you have mixed compression. Actually, I think I might have just drawn mixed. Let's see if I can draw internal. I think internal is just tries this to 1 to a normal. Okay, and so there is this mill standard curve. I think I'm going to harp on here. And it's looking at your pressure recovery, okay, compared to the outside pressure, and it's not perfect. And there's this mill standard that basically draws this kind of quadratic through it. Now, what I want you all to understand, and I also tell my engineers here at Venus, you have to understand that this quadratic fit, this mill standard, you have to understand that this is sort of back in the day where, hey, if I'm an engine person, I need to deal with air that's been gone subsonic, right? All of these jet engines are not supersonic jet engines. The inlet converts the supersonic air to subsonic air and gives you some compression. The jet engines have to start with subsonic air. Now, the result of it is the air is hot and it's compressed. And so the inlet's going to provide this amount. You really need to read this curve, this mil-standard curve, as a quadratic fit so that the engine people over here can be, can run a quick quadratic on their Excel spreadsheet, if you will. Again, you have to frame yourself like 1960s or a quick hand calculation. What is my pressure versus solving all of the isentropic compression with all the losses. Now, it's 2025 when I'm recording this video. I can actually solve for this in my Python script, and like I hit enter, but by the time my finger's off the button, it's already calculated. So so you should look at this mil-standard as a reference. But what I need you to understand on this is that some design choices, yes, will give you something that's junkier than mil-standard. Okay, so if you just have a normal shock inlet, it's going to be junkier than mil-standard, but it might be just fine for a Mach number up to some value, which is what the F16 did. Okay, this is a really easy inlet. More like the F15 thing did this internal compression one, and they have all of these different bleed systems. If you have a chance to go, like I think show some in the book, some of these sort of really mixed bleed where because you can overload your engine at certain speeds at certain altitudes, so you have to have all of these bleeds that do all this stuff. And if you want to see an amazing engine inlet, go look at the SR71. Good gravy. I mean, that thing had so many different bleeds and checks and valves and things like that to sort of adjust it. Again, to keep this engine not only happy, but to have through all of these quote-unquote off-design scenarios that this engine can produce thrust, and it's one of the coolest things ever. They really did. Okay, and it's also possible to exceed this mil-standard through sort of this mixed compression. So don't get too hung up on this thing that's called the mil-standard. Just realize it was a quadratic fit that they did back in the day. And that your inlet choices can be both below it and above it. All right. And then other things, again, you have to take account for. And some of this is, if you hear someone use the word installed thrust versus uninstalled thrust, this is what they're talking about. As a rocket person, this makes almost no sense to me. Like I would never quote my engine as not installed, but I think some of it is just, it's really... I think it's a way of historically, you hear my story about like Bill Boeing and the Boeing days, historically engine is separate. And so the engine is just this core thing inside you. You really need to frame yourself as like, that's Pratt & Whitney, Rolls-Royce, GE saying like, we have this engine and your installed thrust is really onto you, the airframer. Actually, that's the better way to think of this, is why all of this stuff exists. All of this like, installed, and it was sort of that ICD, that the interface diagram, interface control document between company A and company B. All right. And then the last one is boattail. Right. Boattail, which is the drag behind the engine. Right. And it can pick up. So this is Mach. Let's say here's Mach 1. You can have whole variety of sizes, and these curves going this way is A9 over A0. So yes, a small engine will have a smaller boattail, so you need to account for that. Okay, and in some ways, some of this is just because your nozzle oftentimes is not optimal, like your P9 is not equal P0, and so you have that thrust term that doesn't get maximized. The other way to think of it is your boattail. Now, you may actually have your back area be bigger than your back of the nozzle. Sometimes it's just you have to get all of the things in there, the valves and all the engine stuff. So there are times where it's not just a thrust plume mismatch. It can also be just, there is actually a wake behind this engine that you want to account for. Okay, and then go read through some of the stuff there. Where they really they really dig into the sizing of A1. And I'll just highlight to say that there's a lot that you do subsonically, especially towards the higher speeds that commercial aircraft are flying, Mach 0.8, Mach 0.85. there's a lot that goes into sizing this to avoid a shock. So it's a good read. Okay, it's basically here that you're avoiding it right around the lip, because it's not a sharp edge, right? It's a lip. So there's a lot of stuff that they do there to avoid forming a shock. And of course, your aircraft can be at a whole bunch of different angles of attack, right? So really good discussion here on sizing A1. And then, as I already sort of mentioned, your back area can also, the other area of the jet engine is sizing for all the other stuff, like electronics, and you got to cool the electronics. So sometimes like there's actually bleeds and things like that to go cool electronics. There's power takeoff. All these aircraft tend to want electricity to go run all the things that they're doing. So it's not, right? It's not just this engine that's providing thrust. You actually are providing electricity to the aircraft, and so that power takeoff does take up some space. You usually don't see it because it's kind of tucked away in the corner, and it's sort of hidden behind this big area inlet. But you know it's there. There's a power takeoff. Okay, and then I couldn't find this is figure. So in the book, what I'm going to sketch, this is figure 6.E6. So the E means it's the example. It's in the example section, and this is back to Mach number versus alpha, which is your thrust laps. Okay, and I couldn't find any good examples, and so basically it was showing how sort of this is the engine performance, and then this is sort of the installed version, and that this is for military. So mil standard, and this is for max, which max just means afterburner on. I don't know where those terms originate either. If you happen to know, put them in the chat. Mil power versus max power. You know, as a non-fighter pilot, right? I'm just a regular pilot. I actually would have inverted those two. I would have said max power is the max power of your engine, and then military is like punch it, like afterburners on. So, anyways, I would, if someone knows the history behind that terminology, let me know. It'd be really interesting to say. And then, yeah, and there's also they have other ones that like different altitudes and things like that. So go take a look at this figure. Not to steal too much of their thunder here, but they actually do this figure for the engine they're designing, which is the important part. And that's probably why I couldn't find any good examples out there in the open internet. Is some of this is engine specific, and then aircraft and integration specific. Again, in this like off design, installed thrust at non-optimal conditions for the engine, which to me is just hilarious. Okay, and then chapter 7 is actually kind of a quick chapter. It's really like all other things. Now, what do I mean by that? It's like structural loads on the engine, bearings on the engine, lubrication, fuel, controlling the air system during start. Go read through some of that stuff. It all sort of makes sense. We got into some of this in the Rocket book as well, where it's sort of like now for the rest of the story kind of stuff. And so it's all of these things that as engineers we want to say, hey, this is solved, and then you just assume that this thing will work, and then you finally talk to the bearing engineer, and they're like, whoa, this is not that easy, and it turns out to be a pile of work. So it's a good discussion. The structural one's interesting when you took a look at really the loads these engines are under, and some of the design of the struts and all that. Like it's not it's impressive too. So kind of go dig into it, and then we'll sort of finish up here in the next video with sort of the air components. Like I said, this book sort of starts off at the vehicle level, and so then it'll finally, we're now in the next video about to be like just kind of purely at the engine, and kind of finish it up. So, all right, we'll see you next time. Again, read the book, especially the examples, and especially because in this case, you're really seeing the difference sort of as calculated for this engine in the example book, what the difference between installed versus uninstalled, and again, all these off designs. All right, we'll see you next time.